Hello friends, today we will study half-wave rectifiers using PN junction diode. Well, so what do we need rectifiers? Well, in most of the electronic equipments work on DC and every household is supplied with AC from the electrical stations. Hence the equipment that are used in our home will fail to work. Rectifiers convert the AC into pulsating DC, which is later filtered using power filters like capacitors and inductors. What we are going to discuss today is a single phase half-wave rectifier. It is the most simplest form of rectifiers. It is normally used in industrial applications. It basically consists of a step-down transformer, a PN junction power diode, a capacitor filter, and a load resistor. Now, what should be the objective for our study today? Well, the first thing is we will construct a half-wave rectifier using a simple step-down transformer, rectifier power diode. For the filtration purpose, we'll use capacitors and the load resistor. We will vary the values of the load resistor so that we can study the load regulation characteristics of a half-wave rectifier. After the construction of the half-wave rectifier, the load regulation characteristics with filter as well as without filter will be studied. Let's now have a look at the circuit diagram. Well, here we will consider only the positive wave rectifier, half-wave rectifier. Now, as we can see, it consists of three sections. One is the transformer. This is the step-down transformer. The other section is the rectifier, and the third part is the load. Now, in the primary section, we'll be basically connecting the AC supply. And now, in our household, the AC supply is around 220 to 230 volts. In the secondary winding, here we can see that we have a bridge type transformer. That means it is having only two terminals. One of the terminal is the common terminal, the other terminal actually provides the voltage. Now, if we are using a 12 volt transformer, obviously this is at 0 compared to this. So we have labeled the secondary part as A, B, M, and L. Now, the P-type for diode is basically connected with A, and the N-type of the diode is connected to the 0 terminal or the common terminal via a load resistor. Now, when an AC supply is applied at the primary due to mutual induction, the secondary will also have an induced voltage. Now, the induced voltage will completely depend on the number of turns in the secondary winding. Since it is a step-down transformer, we will expect a low voltage to be induced in the secondary. Now, in our case, we'll be considering a transformer having a voltage rating of 12. Now, when we apply the AC voltage at the input, the secondary input voltage will be induced here. Now, in this particular terminal, with respect to the common terminal, we can see that the signal varies from positive to negative, and it keeps going on. Now, let us consider when the situation is that the terminal is positive with respect to this. What happens? If this terminal is positive, the P-type of the diode is basically connected with higher potential with respect to the N-type, which is connected to the common via this load resistor. Now, when this happens, the PN junction diode conducts and it is in the forward bias mode. Since it is in the forward bias mode, current will flow from the secondary through the diode, through the load resistor, and will return to the common terminal. This way the circuit gets completed and a current flows through the circuit. Now let's assume a current flowing through the secondary as IS, current flowing through the diode as IT, and current flowing through the node as IL. Now since the current is flowing from the top of this resistor to the bottom of this resistor, the top portion of the resistor will be at positive potential compared to the lower one. So when the diode conducts, that is, when the input AC is in the interval this, we'll get an output. Now what happens when the cycle reverses? When the cycle reverses, this particular terminal is at negative potential compared to this. So P-type is essentially connected to the negative potential compared to the N-type, hence the diode will get reverse biased, and we all know when the diode gets reverse biased, no current will flow through the diode, hence we will not get any drop across the load resistor. Hence we can say that the input negative half has been clipped or rectified by the diode. Since the circuit only rectifies the positive cycle, we will call it a single phase positive half-wave rectifier. Now let's see the current voltage at the output of the transformer. Now just at this secondary of the transformer, we will get a signal like this. Now it is continuous with respect to time. Now when the signal gets rectified, the time interval between 0 to pi is available, and pi to 2 pi the signal gets clipped at the output. Similarly, 2 pi onwards signal again appears, and again 1/2 of the cycle is missing. Now if we assume this be the peak, then, and if we assume this to be the current, then this is the peak current, and as per the Ohm's law, it will be equal to the peak voltage divided by the summation of the three resistors. Now what are these resistors? RT here is the diode resistance, RS is the secondary winding resistance, and RL is the load resistance. Usually when the diode conducts, this resistance and the secondary winding resistance are almost negligible with respect to the load resistance. Now let us assume the voltage at the secondary of the transformer as this. Now this somewhat resembles a simple harmonic motion. For simplicity's sake, we will be assuming Vi equal to Vm sin omega t, whereas we will be neglecting the phase difference. Now here Vi is the instantaneous voltage, Vm is the peak voltage. So as per Ohm's law, we can very well write Im is equal to Vm divided by the summation of RT plus Rs plus RL. Now what happens if we try to measure the voltage at the output of, or at the across the load resistance? When we apply a multimeter across the load resistance, it will only measure the average voltage. And why will it happen? Let's see. If we consider the current flowing through the circuit as I equal to Im sin omega t, where again I is the instantaneous voltage and Im is the peak, I is the instantaneous current and Im is the peak current. Now we all know from the previous figure that the current to the diode is available when it is between 0 to pi, not available when it is between pi to 2 pi. So current is available when it is between 0 to pi, and current is not available when it is between pi to 2 pi. So now if we try to analyze the current that is flowing through the circuit, we will actually call that IDC, which is nothing but 1 by 2 pi integral I d omega t. Now, if we break down this into 2 parts, that is 0 to pi and pi to 2 pi, we can see that I is available when it is between 0 to pi, and I is not available when it is from pi to 2 pi. Now, solving this equation, we can see IDC turns out to be Im by pi. Now, what about the DC output voltage? We all know the DC output voltage that appears across the load resistance will be VDC, that is the average voltage into the average current into the load resistance. This is as per the Ohm's law, which can be put in terms of Vm by substituting the expressions for IDC and Im from the previous equations. Now, the DC output voltage appearing across the load will then be, we all know IDC is Im by pi, so while substituting the value for IDC, we will get Im into RL by pi. Similarly, if we substitute the value of Vm here with respect to Im, we will get the expression that is VDC equal to Vm by pi by Rs plus Rt divided by Rl plus 1. Now, this expression is very interesting expression. Just if we look into it, the denominator part is having Rs plus Rt divided by Rl plus 1. Now, we all know for a very good transformer, the secondary winding resistance will almost be equal to 0. And when the diode is in the conducting mode, its forward resistance is also very low. So, with respect to RL, Rs and Rt are almost negligible, and hence we can neglect this part and we will get VDC equal to Vm by pi. We always have to remember that if the transformer is of a very good quality and if the forward resistance of the diode is very low, only then this is possible.